And right now I want to simplify the conditions for using these equations. And how to simplify? The one is this. So right now we have the solutions. Solution is there. To simplify the equation is this. For practically for the beam under loading, dy dx is very small. I'm going to explain this. For example, this is a cantilever beam. And here for teaching, for illustration purpose, and if this is loading here, and here I exaggerate the deflection like this. Actually, this one, you can see even for this aluminum, if I can sit down to here, you can see, you barely can see the change, the shape of the deflection, right? So basically here, in reality, this change of the shape should be very, very close to here. So that means in practice, the slope, which means the change of the shape, should be very, very small. So that means this one is almost zero. For regular beams of say the EI, this one is valid for EI, the multiplication of the EI. For E multiply I is large. How large? As large as possible. So whenever you, if you in your practice, if that with a situation like this, then our curvature can be, then this equation 1. Equation 1 can be simplified to a very simple one. Y double prime equal to m over EI. And y double prime is d squared y and dx squared. And that's it. This is the equations we based upon in this class to solve for everything. And this equation is very easy to solve. And let me give you the general equation here. So right now I'm going to review the differential equations. So for this example, dy dx squared times EI will be equal to m. For example, the m general is a function of the x. So here we integrate this equation on the both sides. So here is EI, so this is a double derivative, and after integration, so that reduces the orders by 1. So this is the integrations of m function of x dx. And doing the integrations, we have to come up with the integration constant to consider the boundary or initial conditions. So here we say A here is the integration constant. And to be determined from the boundary conditions. Okay, so now this is the first derivative, so we integrate one more time. So it'll be EI, and then dy dx we integrate one more time, that becomes y of x. And this one will become double derivative m of x dx squared and plus a. Here a after integration, so it becomes a times x. And again here we have the integration will come up with the second differential, the integration constant. So here the a and the b are both are the integration constant to solve for. And that's it. That is the standard procedures for the differential equation you would need in this chapter. Okay. And most of the time in this exercise, the E times I, the EI, multiplication of the EI will be the constant. And sometimes if the beam would not be uniform, then EI could be the function of X as well. So you simply extend the concept for the integrations. So this is the equation we've been using in ES 331. So we can ignore this. This is an exact equation. And this equation can be solved. And actually, if you have, or you'll be taking the, for example, microfluidics, which means talking about the behavior of the fluid at a small scale, then this will be equation similar to surface tension. And that one, we do have the exact solution, but that solution is very dirty, very long way. So, but anyhow, I'll tell you is this: we do have a closed form solution to this problem. To engineering, the most of the case is as long as we make sure the E times I is large, then this equation will be very accurate approximations. And what conditions? Let me ask you, what conditions this wouldn't be good? If you would put plain the bamboo stick, and slip it, and you can see that bamboo is very easily bent, right? So for that case, the bamboo wouldn't be the good model for this case, because that is so flexible, and you easily sweep it, and that will deflect. So that one, if this will be applied to the bamboo, then this equation won't be good enough. You have to go to that way. Yes?
For that equation over there, would it, is y of x, like, why isn't there like a double integral, like, so there's a double integral there, and I understand that, and then you have plus ax plus b, because those two are the constants from the first, like the first,
okay.
Yeah, but on the other side, why is there only, so, okay, so yeah, why is there the integral?
No, here I just want to say do the first integrations, we integrate, and here we integrate. That's it. Okay, later we will use the example you will see. Okay. The second example is if you remember in the old days, the space shuttle they deliver the satellites to the space, and they use the space arm, that kind of three-stage space arm. If you have seen, probably you are too young to see that kind of the movie, to watch that kind of movies. You know the space shuttle is a cargo. There's a cargo, right? They can open up the cargo, and there they have a satellite they can deliver. Once they get into orbit, how can they get the satellites out of that one? They have the three-stage robot arm. The arm is very long, and this three-stage robot arm are made from Canada, and very flexible because they have to make very light. So basically, that space shuttle has this kind of arm. So once they get in the orbit, they have this arm, and to grab the satellite out of the cargo and then put it into space, and that's it. Okay. This arm being made very flexible, very long, and if you've been watching the movies carefully, actually this arm is very flexible. And under that situation, because that is a very hot topic of research, we call it flexible arm or flexible beam, control of the flexible beams. And that one, we have to make sure the endpoint of this movement, and the endpoint is follow what we designed, and in a way to suppress the vibration or the deflection of the beam of the arm. And under that situation, actually people just go straight to this point. that is a very old state, and right now to this young generations, even space shuttle has been retired, right? So that's one, that's an old story. So that, and again, as long as the EI is large, then pretty much we can make sure this will be good. And the remaining topics will be, I will give you the examples to exercise the problems here. So we can try this one. So if this is a beam and under simply supported at Q end, if it is under constant distributed loading, omega 0 equal to constant. Okay, so the length equal to L. So we want to calculate what is y of x. And usually we place the coordinate system is, we place the origin at the left hand side. Okay, that is where we measure the x. So for this case, we try, say, from the bending the shear and bending moment curve from this, that is the we familiar with. So from this case, we have to calculate the reaction here. So for the reaction, this will be omega L2, omega 0L divided by 2. Okay, from here, this you can use the equilibrium equations to calculate both reaction here. Once we have done here, so here that is the equation here. So this is omega 0 or L over 2. So this is omega 0 over 2 minus. So the slope is minus omega 0. So therefore, from here we can see V of x will be equal to minus omega 0 x plus omega 0 L over 2. Okay. And for this one, we can calculate the curve will be equal to, if you remember that one, n will be like this. Okay, so this is a parabolic. And what is the shape of for mx? And in this one, I'm going to calculate in this way. And dm dx equal to v. And here the v equal to minus omega 0x plus omega L over 2. So therefore, from here, the m of x will be equal to the derivative. We take the integration on the both side. And plus the integration constant. So this one, we can do this carefully, is minus omega 0 x squared divided by 2 plus 2 omega squared L x plus a. And because the m equal to 0 at x equal to 0, so that means we know that at this end, there's no externally applied bending, so here the m should be equal to 0. So that corresponding to these boundary conditions, using this one we can calculate a equal to 0. Okay, so therefore for this case, this curve will be equal to minus omega divided by 2 x squared plus omega squared L times x. Okay, so that is the first step. Okay? So this is the first step, and then we simply utilize here this equation. So let me write it out, this equation here. So here we're using is y double prime of x equal to m over ei. Okay, so that is our formulation of the problem. So we continue from here. So therefore, here the d squared y dx squared will be equal to, here we multiply ei to here. And that will be equal to m equal to minus omega squared x plus 2 omega L x, right? Okay, so now we simply go to the integrations. So here we do the first integrations. So here the first integration here is ei dy square dx square and dx. Okay, and this one will be equal to this one. So for the first time, I just try to write every single detail step. So for this one here, we can see, because you can see this, what is this? Basically, this is d dx, dy, dx, and times dx. This is the double derivative of the y, so we can come up with this one. So here we can cancel it. So basically here is ei, dy, dx. And this will produce, this side would produce the integration constant, let me call it A1, okay? And this side will be equal to 2 omega squared, and again, integrate is cubed to divide by 6 plus 2 omega L. And x after integration is x squared divided by 2. This side also have the integration, and that will also have the integration constant, let me call the A2. So why not we simply combine the two things together, and so that will ease our calculation, because they both are unknown, so simply why not we combine into one. So that means here is 6x cubed plus 2x squared plus 8. So I have utilized 8 there, so why not here I just using b. So that is the first equation. So we have the integration constant b need to be solved. But here is the first one. So we still have the derivative here. So we integrate one more time on the both side. Okay. So here the integrate. So here we do the integrations on the both hand sides. So that means the left hand side will become ei. And okay, let me write it out one more time. First time, ei dy dx and dx will be equal to this one minus omega squared divided by 2x3 6 plus omega squared L 2x squared plus b and dx. Okay. Yes, everything will transform there. Okay. And now for this one, we can cancel it. So here is the integration ei, and that is y of x. And again, this one is integration. From here, we would have this integration constant appear one more time. So here is the integration. We do this one, 2x cubed omega. So here is times 6. And x cubed after integration is to the 4th power divided by 4. And plus omega squared x 1/2. And square after integration is cubed divided by 3 plus bx plus c cubed. So again, I integrate the two things together into 3, into let me rewrite here, will be equal to minus. So let me combine the coefficients. So 1248 omega x 24 plus 12 plus bx plus c. Okay, so right now I combine the c1, c2 into c. Here we have two unknowns. Integrations, constant, and what?
Over here, yeah. So over the behind you or in front of you, right there, up one, go up, and then go to the x over 6, x cubed over 6. There shouldn't be a 2 then.
Yeah, you have
in front of
an
it.
extra 2 in there.
Huh?
So you have omega over 2, and there shouldn't be an omega
So
over
it should be
2.
x cubed over 3.
Yeah.
Oh yes, that should be 3. Thank you. Okay. So that should be 3. This should be 3. So this should be 3. So this should be 3. So this should be 24.
Yeah, 24.
Thank you. So this is our diffraction. So you can see y of x has been totally appeared here, as long as we can solve for b and c. So the boundary conditions for this problem is this. The first one is at the support. We're looking for the boundary condition at the support. Okay, that is the easiest way. Look for boundary conditions at the support. At x equal to 0, there's a no diffraction. So therefore, from here you can see EI times at x equal to 0 equal to, we simply plug in x equal to 0, 0 plus 0 plus b times 0 plus c. So therefore, from this, the first boundary condition is c equal to 0. Then at x equal to L, y equal to 0. So this one, you need a little bit calculations. So EI times y equal to 0 will be equal to, when x equal to L, omega 24 times L to the 4th plus 12 omega L, L3 plus b times L. So from here we can solve for b. B will be equal to, here, let me write it out here. B will be equal to 24 omega L4 minus L3, 12 omega L. Okay, so that will be equal to minus okay, so finally we have these things here. Hope my